it can be slightly on the more basic side when it comes to actually the approaches for multivariate data, but we do cover some important concepts throughout the seminar. Okay, so what is multivariate data? When we talk about multivariate, we are saying that there are multiple responses or outcomes per unit. So whatever your unit is, if it's a person, a plant, and we'll go through more examples. And typically these responses are correlated, so they have an association with each other, and the responses might represent different properties of the same underlying construct or unit. So for example, if I was just looking at the shape of humans, maybe I have taken the measurement of my forearm, my femur, my circumference of my waist, and we can think of all of these measurements as trying to capture the shape of me or you in general, and we can think that these are correlated. So that's an example of multivariate data. Not to be confused with multivariable data, where we have more than one predictor or explanatory variable. If you did come to this seminar thinking we were going to cover multivariable data, then I'm sorry to disappoint you. But there is a seminar that goes through a few do's and don'ts of multivariable regression. I'm going to try to hide that for here. Okay, starting off with a simple toy example. I want to know, does organic fruit taste better than non-organic fruit? So we can think, we all know fruit. There is not just one fruit, and we have many different types of fruit. So, but my question is, well, does organic or non-organic taste differently? So what I might do is I might go out and collect some data that we are measuring the taste of the different types of fruit. So for example, I have strawberries, blueberries, oranges, lemons, apples, pears, and bananas. And we can think of these all as a collection of trying to represent fruit as a whole. And what we might expect is that also fruit might be correlated as well. I'm going to say that berries might be more similar to other berries, although I did recently find out that strawberry is technically not a berry, which is very confusing. But in my brain, it is a berry. And we have our citruses together, and we have our apples and pears. That's how I'm grouping fruits in my brain. And then we have banana out all by itself. So when we're looking at this data, we want to combine all of the responses together and answer collectively, do organic fruits taste better than non-organic fruits? And typically when it comes to multivariate data, it's typically, I'm bringing this up just because this is more of a technical when it gets down to analyzing it. We typically store it in wide format. And what we mean by wide format is that each row can represent a sample or replicate, and we have stored the responses in columns. So here we can see that we have each of the fruits in their own columns, along with any predictors of interest as well. So here we have 7 response variables. Okay, now going back, covering some more multivariate data that you might see in your research, and it does pop up in lots of different places. In psychology, they use a lot of scales trying to capture emotions or well-being. So for example, a WHO-5 well-being index has 5 questions trying to capture somebody's well-being, and we have chronic pain acceptance where there's 20 questions. Emotion thermometer, where you're trying to, again, capture somebody's emotions. In ecology, we might be looking at the species community as a whole. So you might go out and collect the count or the number of species you might observe at sites. Or maybe you're looking at species traits. So it could be the length and width of a flower petal. Here it was first flowering day, last flowering day, flowering duration, although that's a function of the first two, and the day of peak flowering. And then in chemistry, we also come across this a lot when we're looking at maybe the chemical components of whatever subject you're looking at. And here it was just coffee beans under different roasting conditions, if you're interested in coffee, or lipids as well, which you're looking at the organic matter as well. So all of these, you might have multiple responses, and we might be trying to do some hypothesis testing about the collection of these responses. Okay, so now that we know what multivariate data is, we want to know, well, how do we analyze multivariate data? And there are different strategies of analyzing the data. So suppose, for example, we want to test or look at the association of a predictor and the responses. We might look at, well, can we actually analyze a single response? Or can we analyze the responses separately and control for multiple testing? Or can we actually just do multivariate analysis? And I'll go through each of these approaches. This seminar came about in my brain because when I moved to non-ecological data, I was like, what do people do in other fields? And I brought up all of these different approaches, and the general consensus was, yes, they're all good, and the classic answer of it depends on your research question and lots of other factors. So I'll be going through some pros and cons of each of these. So the first step is, well, or our first question is, do we actually need multivariate analysis? I'm going to say, go back to my fruit example, and I actually am more interested in saying, well, actually, I'm interested in just fruit salad in general, rather than just fruits individually. So then I can just compare the taste of fruit salad, organic and non-organic. And that way we've reduced the whole question down to just one response variable, which is the taste of a fruit salad. And in general, this is probably the first step that you might do, is like, okay, actually, multivariate is hard. Can I only analyze one response? And it can be meaningful when that is the measure that you're primarily interested in, and if a univariate response can actually summarize that underlying concept or construct that you're interested in answering. So there are different ways that people go about to try to make a multivariate problem into univariate. In psychology, a lot of the time they have, while they have multi-item scales where you answer 5 questions, they come up with a way to get a total sum of that questionnaire, and then you have only a single score for all of those items. So for example, going back to the WHO5 well-being index, instead of just analyzing those 5 questions, you can sum up the responses of those 5 questions and just analyze that total score. In ecology, instead of looking at the abundance of each species, what you might do is you might summarize using species richness and just count the number of species at the site. And that captures the overall diversity. So you would use this approach if your univariate summary or characteristic is what you're interested in. But if you're interested in knowing more about each of your response variables, then this is not appropriate. So why is this good? Well, once we've made our multivariate data univariate, then we can just use our usual methods that we see for univariate or single response. For example, if we have a quantitative continuous response, we might try to fit just a linear regression model where we have our response is normally distributed and the errors from the model are normally distributed with constant variance. And we have the relationship between the mean and each of the predictors is a linear relationship. And I've split this up here in case you don't like maths. We're just modeling the mean, which is your line. It's a constant, that's your intercept, and the slope of each predictor, depending on how many predictors you have. If you're not familiar with linear regression, then we can actually think about, well, might help you to think about it as a special case of t-test, and we have a seminar going through that as well. And for all our models, we like to check our assumptions, and we also have a seminar on checking assumptions. So that's by Gordana. And one of the assumptions here is that we're assuming linearity, and what happens when that doesn't hold, maybe you have a nonlinear relationship. Well, Ben goes through approaches to handle the nonlinearity relationships. Okay, so the advantage of univariate is, well, it's now simple to implement. We just have one single response and we can use our regression methods that we might be more familiar with. We've reduced the dimensionality and it's easy to interpret. The limitations is, well, sometimes it can be hard to actually construct that single univariate response. It's easier if you're dealing in psychology, for example, if you're dealing with a validated scale, and we know that that one total score is summarizing just that one underlying structure. For example, if we go back to well-being, if it ends up that one is kind of capturing well-being and one's capturing, I don't know, your health, like your physical health, then it wouldn't be good to just use a single total score for that. That's slightly exaggerated, but we just want to make sure that it's only measuring the one underlying structure. And the other thing is that if there is a difference, we don't know where that difference is coming from. We don't know if it's just one single response or multiple responses. But you can do further analysis for that. Okay, so that's step one. If you can skip the hard stuff, try to do it. Otherwise, we have the other two approaches where the first one is you can run multiple univariate analysis. So if we're interested in knowing the relationship between your predictors and each response, or each response, then you might want to model each response separately. And there we're still doing univariate analysis, but running it multiple times for each response. And because we're running multiple models and doing multiple tests, then we need to control for running the multiple tests, because the more tests we carry out, the type 1 error rate increases, where the type 1 error is a false positive. So we're finding that there is an effect when there's not actually an effect present. The type 1 error rate, if we have P here is the number of responses. So going back to our fruit example, 7. Actually don't know what it is, but we can find out what it is. It's probably between 30 and 40%. So instead of the alpha is equal to 0.05. So that's without adjustment. So what we should do is we should control for the amount of tests we do. And there are different methods that we can use to control for the family-wise error rate. The simplest one is the Bonferroni, which people might be familiar with. And when it comes to using these methods to control for multiple testing for correlated response, we actually will probably have lower power, especially if the responses are correlated, and it will be conservative. So you'll just have a less powerful test if you carry out multiple univariate analysis with controlling for multiple testing. So that might work if you have only a few outcomes and they are not strongly correlated, if they have small correlation. If they're strongly correlated and you want to increase the power, then we could conduct a permutation test. I'm not going to go through that. You can check out Eve's seminar on strategies for dealing with multiple comparisons if this is your first time seeing how we can deal with multiple tests. The other thing that happens when we look at all of the responses separately is that you might miss patterns that only appear jointly. So this is just a made-up toy example again, where we have diastolic blood pressure and systolic blood pressure. And we have control and treatment. In this one, I would say it's still hard to find a difference, but it's there. When you look at it univariately, you're saying that the groups don't differ that much. But when you look at the response variables jointly, you can see that the blue line more or less lies above the red line, or like the blue dots, blue points lie above the red points most of the time. So why would you use this multiple analysis approach? Well, again, it's simple to implement because we're using our standard regression methods that you might have learned in Intro to Stats. And the other thing is it can easily handle multiple response types. So if we have a continuous response or an account response, then we can model those separately and handle or deal with the different distributions of those response variables. And again, when it comes to interpretation, it's just we can go back to our it's just easier to interpret if it's just one response. So the disadvantages, the main one is that you have lower power when it comes to this approach. And sometimes if your variables are strongly correlated, then you might miss some structure in the data by looking at them one at a time. It can get time consuming if you have a few responses, because you have to, like, it just gets a bit clunky if you're dealing with lots of model outputs and checking everything. Not that it's not doable, but I think you can make a lot more mistakes if you have multiple models and you have to look at everything individually, and it just, I think it's, more time consuming. Okay, so you might have come to this seminar just to learn about multivariate analysis. So we're finally going to get to this method. The idea of multivariate analysis is instead of running many univariate models, we want to model the responses jointly, and that's all together at once. The one thing about multivariate is it is hard because we've suddenly gone from one dimension to p dimension, and that means that there's a lot more things that can be going on, a lot more different relationships, a lot more different forms of relationships. The assumptions may be violated more. It can just get harder to fit because we have a lot more, we'll get to that, we'll have a lot more parameters to estimate. So the complexity can grow quite quickly as the number of responses increases. So depending on the multivariate data you have, and what I mean by that is it might be how many response variables you have, how many samples you have, what's the study design, do you have dependent data other than your correlated responses. Then, depending on all of those factors, you might choose different methods to analyze your multivariate data. So the simplest one is MANOVA, where MANOVA is the multivariate extension of ANOVA, which hopefully most people know about, where you're just comparing means, but you're comparing now a vector of means of your responses. We have mixed models with a multivariate random effect. I'm going to go through that. We have more approaches where we're reducing the dimensionality in a factor analytic approach. So you have factor analysis for multivariate normal data, or you have generalized latent variable models if you have a non-Gaussian response. If your number of response variables it approaches the number of samples you have, or even more than the number of samples you have, you might go to a design-based inference. And again, I'll go through what all of these mean. So the advantage of multivariate analysis is that we are improving our power. We are properly accounting for the correlation between the responses, and we have more efficient parameter estimates as well, because we're sharing across the responses. So MANOVA, we can think about MANOVA as fitting many linear models where you estimate a vector of p means, where p is the number of responses. So going back to our fruit example, we had 7 fruits, so we're going to be we're basically fitting 7 linear models, but there is an assumption in this model that the responses are jointly multivariate normal. So we've gone away from our 1 dimension to p dimension. And this is where multivariate becomes hard, is that we have now a variance covariance matrix, and that's what that's what parameterizes a multivariate normal. And I'll cover that in a second. But again, what we have is we have now, instead of just looking at one mean for our one response, we're looking at p means. So mean j is the jth mean for the jth response. And we have, again, just our linear relationships again. The thing about a MANOVA is that we can actually just fit a multivariate linear regression model using our lovely LM function in R. But instead of just having a single response variable, we now have a matrix of those responses. And I'll be going through an example in a second. So what is multivariate normal? Well, multivariate normal extends the normal distribution so that we have now a vector of means, and we have a variance covariance matrix, sigma. And what is a variance covariance matrix? Well, it extends the variance to multivariate dimension, which captures both the variance of each variable along the diagonal, but also the pairwise correlation between each of these variables. So this is how we account for the correlation between our responses. And if you're not familiar with covariances, covariances are just correlation, which, correlation is just on your -1 to 1 scale. Covariance just rescales it to the original units. Yeah. So that is a MANOVA. We can think of it as just multiple linear regression models, but we're assuming our response is jointly multivariate normal with instead of just a constant variance, we now have a constant variance covariance matrix. I am briefly mentioning the other methods, and it's brief because this is complex and it gets hard. Not hard. It contains a lot of information in few words. That was a MANOVA. That works again in the same cases that you might work for just a ANOVA or a linear model. That it's for if you have independent samples. The minute you have not dependence, you again have to go into your mixed models approach. So you can then you can still analyze your multivariate data in a mixed model, except now you need to account for the correlation between your responses. And I have an example at the end. And then you can count for your study design factors as you usually would in the univariate case. You just add an extra random effect into your mixed model. So that's if you have a few responses, and sometimes this, again, depends on the sample size you have. It will probably work for 2 or 3 or 4, maybe, depending on the number of samples. But that quickly becomes too complex to fit with your standard, with your full variance covariance matrix. So there are the dimension reduction techniques, which are the factor analysis or generalized latent variable models. And that just reduces the dimensionality of that variance covariance matrix. So instead of having a P by P variance covariance matrix, you now have a P by D, where D might be like it's much less than P. It might be 1, 2, 3, and so forth. And you might be familiar with factor analysis from psychology, for example, for developing instruments or looking at those total score or those underlying constructs. But we can use that as well for just analyzing any multivariate data, as long as we can assume multivariate normal. And then for very high dimensional data, that's where P is approaching your sample size or greater than your sample size. Well, in a lot of the cases when we can't assume a model or a distribution, well, we normally use bootstrapping or permutation to get us out of those tricky situations. So we can use the design-based methods for inference. And the thing about this is if you have, again, extra dependence in your data, it can become very challenging to know how you're supposed to permute your data or bootstrap your data. So that becomes tricky under certain scenarios as well. And it's also can be computationally intensive. Okay, so I've gone through a lot of things in a very short period of time. So I'm just going to show you a simple example where we're looking at gender-related attributes survey. This is a survey which consists of 6 scales, and even these 6 scales themselves are from multiple items, but we're using the I think average score from those scales or something like that. I didn't look into it, but we have, so within the scales, there's multivariate data, but we've made it univariate, but we still have 6 responses. So these 6 scales are trying to capture gender-related attributes, and it's across 3 domains, which is personality, cognition, activities, and interests. And each participant receives a score on these 6 scales. And what we're interested in knowing is, well, are males and females, is there a difference between males and females on these scales? I mean, it's in the name of the scales, so there should be a difference, but we're going to just do it as an example. So I'm just showing you the data here. Again, we have the data in wide format. So again, the response variables are represented in columns, and we have a column for gender, and the rows that just identifies the sample. So this male is different to this male. So we have independent samples but correlated responses. Okay, so how correlated are these response variables? We can just do a look at the correlation and maybe put some colors on it. They're not highly correlated. So in theory, we can maybe do multiple univariate analyses on these 6 scales. However, we would need to we would need to control for those 6 tests if we're testing gender in each of those models, because we want to know whether overall there is a difference between males and females on these attributes. So so we'll have lower power if we look at these individually. So I want to look at them. I want to test it jointly, and we're going to use MANOVA to test them jointly. So to jointly test for an effect of gender on the 6 scales, we can fit our multivariate linear model. So again, going back to our linear model, but our response is now the matrix of our 6 scales, and we just have gender as a factor as our explanatory variable. And we can see from this fit, we have as usual, we have the intercept and the coefficient of our factor, but we have those estimates for each of those scales. So now we can get the means for the males and the females for each of those scales. And what we want to do is we want to test whether those means are equal for males and females. And then, so what we can do is we can perform a multivariate test, and there's different tests we can conduct, but the Wilks test corresponds to running a likelihood ratio test. So that's the test that we choose for here. And we can see that there is a difference amongst males and females and their gender or their attributes, which is not shocking, but it's good to know. If you ever run a model, you should always check the assumptions. I didn't go through the assumptions, but they're very similar to a linear model, except we have the added residuals have constant variance covariance. To check for multivariate normality, normally what you want to do is you want to fit a single response against all of the other responses and all of the other predictors and check if those assumptions are satisfied for that model, and you run that for each response. Thankfully, David Wharton wrote a function which does that all for us. So we can just use the plot envelope function from Ecostats to check the multivariate normality assumption. And again, we're looking for our constant variance covariance matrix, or constant variance, and the linearity between the mean of each response and each predictor. So here we can see that there's a constant band across, so our constant variance covariance is fine, and there doesn't seem to be any nonlinear relationships. You can probably go into this in more detail by plotting a smoother for each response and check for each response and each predictor. So this is what I mean when we're in a multivariate world. Straight away, there's a lot more assumptions going on. There's a lot more checks that we have to do. Maybe we'll have nonlinearity for one response and so forth. So it can quickly become a whole process. Just for the sake of showing you and kind of just giving you the way to do it and not going through the nitty-gritty details, we can do the same thing in a mixed model. And for most mixed models packages, the data needs to be in long format. And that's why I've gone through wide format and long format. So here we now only have 2 columns. One tells us which scale the observation corresponds to, and we have 1 column with the actual response to that scale. This is just formatting the data. It's part of the process as well. So this is just in long format, and once it's in long format, I can now fit it using the mixed model package glimtmb. And I've titled this the dimension reduction because if I tried to fit a full variance covariance matrix, the model wouldn't estimate, it wouldn't fit, because even at 6 responses, it was struggling. So we used the factor analytic approach here, which you can specify using or, that's the reduced rank. So that's just reducing the dimensionality of that variance covariance matrix. And again, here we have, like any regression model, we have our response, which is y. Even though it's multivariate, we've accounted for that in the random effect, which I'll get to. But we're specifying scale that that corresponds to the mean for that scale for whatever gender, reference gender that is. So the males or females, males. So that's just your intercept. And then here you have your slope parameter for how the gender differs compared to the other level. And this is how you fit the random effect to account for the correlation between your response variables. It's just a standard way of fitting this random effect where you have the intercept for that scale that varies by your samples. There is some documentation of going through this. If you're not familiar with this, I wouldn't worry too much. Come see us if you want to know more about fitting those multivariate random effects. And we can get, again, just the correlation between those. Again, we're accounting for the correlation and we're estimating the correlation between those scales. And we can now do inference on the model output like we would in univariate analysis. Okay, so that was a lot. I think the takeaway here is that depending on your research question, you might use the different strategies. If you can go univariate, that is the easiest way, but you need to make sure, is this the just capturing one underlying characteristic that you actually care about, or do you want to know more about the different the responses? If so, if you have only a few response variables that are not strongly correlated, then you might be doing multiple univariate analysis and accounting for the multiple testing. However, quickly, if your response variables are more than a few, and depending on the study design, you will use different approaches. So the MANOVA, that's when you have independent samples and a few responses. And you can go to the mixed models, again, for similar few responses, but you might have dependency in your samples. And then quickly, you might need to reduce the dimensionality of your problem. So you can go into factor analysis or generalized linear latent variable models. Otherwise, if you have high dimensional data, you will need to go to your design-based methods. Any questions?
Something in the chat.
Yeah, MV-Abun falls into the design-based methods. That uses resampling or permutation.
Dimension reduction you mentioned earlier, for RR, so it used to reduce the dimension of the data set.
No, of the variance covariance matrix, not like, so you still have your however many responses, but it's how you estimate the correlation between your response variables. Instead of like your large P by P that I showed you, it will be much smaller, the dimension, but it would still be approximately like capturing that correlation.
So R is based on like which kind of like principles?
Factor analysis, but that's in the multivariate normal, and it's also known as generalized latent variable models when you go into non-Gaussian responses. Yeah.
Also, this models based on like the normality of the data, because I feel like most of the models are like linear based.
You mean Gaussian or?
Yeah, Gaussian, like normal distribution.
Yep.
Test. So do we need to do like the normality testing before applying it?
Oh, so if you're worried, question was if the data is, or a lot of these models might assume normality. How do we need to conduct tests to check for normality? You can use your residual diagnostic plots to check for the assumptions of the model, depending on the properties of your response variable. For example, we might say for count data that has zeros in it, we wouldn't assume that it's normally distributed. We might assume that it needs a Poisson or negative binomial distribution. So it depends on the property of the response. If it's continuous and you might need to fit the model to check if it is multivariate normal. Yeah.
I have a bit of a beginner question. So when you're modeling, like let's say you have two responses, so you have a choice between modeling like univariately or jointly. When you model it jointly, is there ever like a pair of maybe like you have some of your main effects kind of getting absorbed into that correlation coefficient? Is that something that can happen?
So because they're highly correlated,
like it's maybe hiding
the effect.
Yeah.
Well, there you might be able to test whether or not the effect is different by response jointly. Yeah. But then it's like, well, if the effect is, if they're so highly correlated and there's an effect on one response variable, then it's going to probably affect the other response variable because they're so correlated. Mm-hmm. So it depends on what, are they responding in the same way? Yeah. I think there's a. Oh, okay. Great. Thanks, everyone. Thanks for coming.
Yeah, I thought it's like it's very nice.
you thinking of a scenario where it's a picture?